All right, so we've been able to successfully look at dimensions of space and natures of space. We've dealt with both absolute and relative, and also Euclidean and non-Euclidean geometry. Now we're going to enter into time, into properties and certain things we need to know about time if we're going to understand fully what we mean by space and time in this context. The first thing I'm going to tackle is the concept that joins space and time together. As we've seen before, most things we do in calculations, since we deal with 3 dimensions here, length, breadth, and height, we'll have 3 axes, x, y, and z, for each of those respectively. And remember, we also said that time is a dimension of t. So what happens when you deal with relativity and space and time is that you get 2 of these join, that is space, x, y, z, and the t of time join to form what is called space-time. Space-time. So you may see this as space-time continuum in some sci-fi sense, but realistically this is called space-time. So it's a 4-dimensional nature that combines both space, x, y, z, and time. So you likely will come across this as you get more advanced or get into deeper calculations in this. So that aside, we've been able to conquer that. We're now going to look at natures of space. That sounds also a bit similar to what we did in we're going to look at nature of time. That sounds a bit similar to what we did in nature of space, and it's going to have the same 2 categories. The first one is absolute time, and if you can guess, this was proposed by Isaac Newton. So the same thing with space. He believes that time is absolute, fixed, and unchanging for everyone, irrespective of where you are. Everyone, everywhere, moving at any speed whatsoever, will experience time in the same way. That's what's meant by absolute space. But the exact opposite is relative space. And this comes almost directly as a result of Einstein and his work on relativity, particularly special relativity. So what we mean by relative time by Einstein, which is what we do, which is what is used now, is that time is dependent on the observer. Time is not absolute, time is not fixed. It depends on the conditions of the observer and also what is being observed. So we'll get into more details of this later, but just to understand the two different natures of time. Absolute, which was previously held up until about 1905. Then Einstein published the theory of special relativity, and we understand now that time is not fixed, it is relative and it depends. So we'll definitely explain this further as we go on. But in a nutshell, what this means, or what you can think of, is that one of the main theories from relative time is that Einstein says the faster an object moves, the slower time passes for that same object. Nice. So this is a term you may hear called, you may hear this being termed time dilation, and it means the same thing. Time dilates for fast moving objects. When things move really fast, we're not talking about 200 or 400 meters per second. We're talking in the order of speed of light, measurable to the speed of light. So when things move at that speed, time becomes relative to them and is slower to stationary or slow moving objects. So we'll definitely even get into calculations on these. But first we're going to look at the postulates of special relativity. This is Einstein. This is Einstein's work. About the year 1905, he came forth with this theory of special relativity that shattered what was previously understood about space and what was understood about time. So there are two postulates. A postulate is a ground assumption, is a basework assumption that holds a theory together. So every theory will have a postulate that kind of holds it up. What do you assume in this theory that makes it work the way it does? So the first postulate of special relativity, that's one, is that all laws of physics are the same. All laws of physics hold in inertial reference frames. We're going to need to break this down a little bit more. An inertial reference frame is a reference frame that does not accelerate. So let's define that. Inertial, RF, means reference frame, does not accelerate. That means A is equal to 0. So when we're dealing with physics, we will have what we call reference frames, which are the lens through which we look at situations. We could be, let's say there's a race going on. There's a 400-meter race going on in a stadium. And we can look at the reference frame of someone on the stands. We can look at the reference frame of the whistle on the umpire. We can look at the reference frame of one of the athletes. And we can also look at the reference frame on the ground. So with each of these different reference frames, you will have different values, different outlooks, different parameters for different phenomena. Okay. So what this first postulate of special relativity means is that in every inertial reference frame, that means for every reference frame that does not accelerate, which means that the velocity doesn't change. So an inertial can mean that my velocity stays at 0 meters per second. And it could also mean that my velocity stays at 25 meters per second constantly over time. Both of these means that whatever I'm looking at does not accelerate. So let's say I throw a ball vertically upwards. And it comes down straight down. Let's say it takes a time of 4 seconds. It takes a total of 4 seconds for this to happen. If I were to mount a spaceship, a very competent spaceship that moves at, let's take a really fast speed. Pew, 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 pew. Let's say my spaceship is moving at 400 kilometers per second. Okay, so it's moving upwards, but the acceleration doesn't change. It means it's not getting faster, it's just moving constantly at this speed. And I throw this ball up, it goes straight up and it comes back down. It will still take exactly 4 seconds for this to happen. And that is the first postulate of special relativity and what it means. It means that for any reference frame that doesn't accelerate, any reference frame that doesn't get faster or slower, all laws of physics hold. That means if I were to stand in this spaceship and do any sort of physics experiments, throw a ball up, dance, turn around, spin, anything you can think of, it will be the exact same thing as if I was standing perfectly still. Alright, so we're able to tackle the first postulate. We're going to look at the second one, which talks about the nature of the speed of light, which is a really cool concept to understand. Postulate number 2 states that the speed of light in a vacuum remains constant. So we need to understand why this was such a big deal. The belief was held, not even belief was held. I'm about to give an illustration. if I stand here and I throw a baseball, I throw a ball to you at 2 meters per second. Okay? Whoever catches this ball, as long as he is steady, will also receive the ball at 2 meters per second. Let's neglect a lot of things: drag, air resistance, and wind. So if I stand stationary, okay, and throw this ball towards the catcher at 2 meters per second, he receives it thrown at 2 meters per second and received at 2 meters per second. None of us are moving. Neither the catcher or the thrower are moving. So consider this scenario where the catcher is atop a skateboard. It's spaceship. The top is skateboard gliding at, let's say, 5 meters per second. Let me draw this down to you. So the skateboard is moving forward at 5 meters per second. And he throws the same ball at exactly 2 meters per second as he did in the first case. You would observe that due to addition of vectors, that it was thrown at 2 meters per second, but it gets received not at 2 meters per second, but 7 meters per second. When you're dealing with vectors, two vectors moving in the same direction gets added, so they become more in that sense. So he doesn't receive it at 2 meters per second, he receives it at 7 because the source is moving. But the same thing does not happen with light. Irrespective of how fast the source of light is moving, the speed of light is always going to be the same constant value, which we call c, and that is approximately equal to 3 times 10 raised to the power 8 meters per second, which is really fast. So these are the two postulates of special relativity. The first one is that all laws of physics hold in all inertial reference frames. So standing in a non-accelerating body, every physics scenario, every physics experiment carried out will be the exact same thing as though the person carrying the experiment was carried out in with no motion. And the second one is that the speed of light in a vacuum remains constant, which is 3 times 10 raised to the power 80 meters per second. And we've been able to see why that's such a big deal. Okay.